The X in VXLAN doesn't stand for extra. Or xylophone, by the way. By the end of this video, we will be able to describe how the SDA data plane functions with Virtual Extensible LAN, or VXLAN. The X doesn't even stand for a word that starts with X. It stands for extensible. We are extending the concept of VLANs by taking a space of 4,000 VLANs and giving us 16 million separate network segments. Well, VXLAN is good for more than just segmenting VLANs. We can actually use it as a tunneling mechanism. And what we're about to find out is that VXLAN solves that problem that we had, as mentioned in the last video. Let's talk about this concept of tunnel encapsulation. If we're going to encapsulate a packet, what we're going to do is we're going to take that original packet, and that packet usually has an Ethernet header on it, it's got an IP header on it, it has some sort of layer 4 protocol, that's sometimes TCP or UDP, and then we have the actual data itself. Well, in many cases, when we're encapsulating, we're going to take the original packet and wrap it in another header. However, we don't need, and oftentimes don't keep, that Ethernet header. So in the case of Lisp, for example, which we mentioned in the last video, we can tunnel using Lisp. So what Lisp is going to do is it's going to wrap this original header here and treat that as if it's data, the entire thing, including the old headers, which means we're going to build a new header in front of it. That new header will have its own IP and, in this case, UDP headers. And so we have replaced the original Ethernet headers with new UDP IP headers, and then we're going to put in front of that a new Ethernet header. So the problem here is that we have replaced the original layer 2 header with a new layer 2 header. And this is why we can't leverage Lisp in an SDA space, because we need that original layer 2 header. Now you look at another tunneling protocol like OTV, and OTV is layer 2 only, and that's good, okay, we need layer 2, but it can't do layer 3, it can't do VRFs and such. And so a lot of tunneling mechanisms fall short for what we're trying to accomplish. Well, fortunately for us, there is a tunneling mechanism out there that can do layer 2 and layer 3. And that mechanism is what we've already talked about many times. VXLAN, the Virtual Extensible Local Area Network. Now, VXLAN was designed to solve a lot of service provider problems, such as scaling in data center spaces. And in the nature of scaling out in data centers is we need the ability to traverse layer 3 traffic, again, mentioning VRFs and such, while maintaining the original layer 2 headers. And because of this, VXLAN was a great tunneling mechanism to deploy within software-defined access, to give us all of the layer 2 and layer 3 functionality that we need. So unlike Lisp and many other tunneling mechanisms, we're going to take the entire frame as the payload. And then VXLAN is going to add a UDP header, because it's UDP based, and then a new IP header, that will be the new source and destination addresses from an IP perspective, so specifically those RLOCs, and then a new Ethernet header. Now, you may have noticed I left a gap there, and the reason for that is because we need a space for the new VXLAN header. The VXLAN header is going to carry all kinds of information in there, and specifically information that pertains to software-defined access. Now, aside from some flags that indicate what type of information is in the payload and such, the VXLAN header is going to carry a couple of pieces of information that are important. One is the VNID, the Virtual Network Identifier. Sometimes it's abbreviated VNID, sometimes it's abbreviated VNI, you'll see it both ways. This is essentially the new VLAN ID. So remember, VLANs, we had, 0 to 4095? Of course, 0 and 4095 were reserved, so really our range is 1 to 4094. So we had 4,094 VLANs that we could use in the space. And this amounted to a 12-bit value, so we had 12 bits to store our VLAN IDs. Well, the VNID is 24 bits, and that means that we have the entire range from 0 up to roughly 16 million VNIDs that we can have in our environment, so scaling is no longer a problem. But on top of that, Cisco actually enhanced VXLAN to call it VXLAN-Group Policy Option, or VXLAN GPO. This has been submitted to the IETF, but really it's just a Cisco extension to make VXLAN work for them in a software-defined access environment. So remember in SDA, we talked about that policy plane. We're going to be talking about that more in the next video. The policy plane is how we identify traffic and enforce policy against that traffic. In order to do that, we need a special tag. Now, spoiler alert here, that tag is something we call a Scalable Group Tag, or SGT, and that is stored inside the VXLAN GPO header. Cisco was able to get 16 bits dedicated for the SGT, which means we can go up to 64,000 SGTs. Now I know 16 bits gives us 65,535, but for whatever reason Cisco cuts it off at 64,000. The range is typically 0 to 64,000 in the software. So now let's take a look at our network fabric, and we recall that we have these RLOCs, which are typically loopback addresses on whatever these devices are, layer 3 switches, routers, etc. And VXLAN has another word for these. These are called VXLAN tunneling endpoints, or VTEPs. So RLOC and VTEP, they really mean the same thing, and the terminology will differ depending on whether we're talking about SDA-specific applications or VXLAN applications themselves. Either way, we're going to form these VXLAN tunnels through the fabric. And this will give us direct communications with each other, not only over layer 3, but over layer 2 as well. Meaning that we can go back to that conversation about having endpoint identifiers or IP addresses in subnet A. For example, we might have IP A1 and A2 at this location. And then up here, off of this router, we're going to have A3 and A4. All part of the same subnet, but as far as A1, A2, A3, and A4 are concerned, they're all on the same broadcast domain as well. So if A2 sends a broadcast, A3 and A4, these will get that same broadcast. Now, one point of clarification is that I know we've been a little down on Lisp here, talking about how Lisp can't do layer 2 over tunnel mechanisms. Keep in mind what we said in the last video. Lisp has a control plane element and a data plane element. That data plane element is the only limiting factor where we can only do layer 3. So we're going to bypass the data plane component of Lisp and leverage VXLAN instead of its own tunneling mechanism. However, we absolutely are going to rely on the control plane elements of Lisp. So everything we've learned about Lisp up until now is absolutely valid. That's all the control plane mechanisms. We're simply going to rely on VXLAN instead of its own native tunneling. Now this is everything we need to know about VXLAN as far as SDA operation is concerned. However, if you're itching to know more about VXLAN, then you are in luck, because we're going to be going into a lot more detail on VXLAN in a future skill within the Encore series. And with that, you're able to describe how the SDA data plane functions with VXLAN. I hope this has been informative for you. I'd like to thank you for viewing.